This video will demonstrate how to factor four-term polynomials. So first, what is a four-term polynomial? The name is pretty self-explanatory. You have a polynomial with four distinct terms. Here's a couple of examples. So you can see these are both polynomials. And then I have 1, 2, 3, 4. So there's four terms. And again down here, 1, 2, 3, 4. Remember, terms are algebraic expressions really that are separated by plus or minus signs. So these both satisfy the category of four-term polynomials, and we will demonstrate how to factor those. We're going to use a process called grouping. Most four-term polynomials, in the context of a college algebra class or an intermediate algebra class as well, will utilize this process called grouping. There are some four-term polynomials that is not the case, and I'll highlight those at the end of the video. But for the most part, if you see that you have a polynomial and it has four terms in it, you want to try to factor this by grouping. If that doesn't work, then that will cause us to go look at an alternate methods. And then don't forget, even though we know that these are four-term polynomials, we still need to go through the general factorization process, which says we need to make sure we're in descending order, pull out a GCF, greatest common factor if applicable, and then go address the specific type. Okay, so if we look at this first polynomial, and let's check descending order, we can see that as we look at these powers on these individual terms, this is the cube, the square, the first power, and the coefficient. So these powers are going in descending order, and so we are good for step number one. Now, can we pull out a GCF, or a greatest common factor? Again, if we look at these terms, these first three have x's, or a variable. This one does not, so we are not going to be able to pull out an x. But if you look at these numbers carefully, we can see that they're all even, which means we're going to be able to factor at least a 2 out. In fact, because this one is the number 2, that will in fact be the greatest common factor that these numbers all have in common. And so the first thing I'm going to do here is actually to pull out a 2. So let's pull that 2 out front, and then recall, I'm going to go ahead and put some brackets here. Recall that when we factor out that 2, it's as if we're dividing each one of these terms one at a time by that GCF, and the result of that division will be the portion of that term that remains inside of these brackets or parentheses. So if I pull the 2 from this first term, I'm going to be left with an x cubed. There's my minus sign. If I pull the 2 there, I have a 6. X squared is what remains. Here, dividing that by 2, I'm left with a plus 2x. And then finally, this last piece, if I divide that by 2, I'm left with negative 12. Okay, so this is actually now the four-term polynomial that I'm going to go ahead and go factor. And then as I progress through that, this GCF will sit here out front as a part of that factorization. Okay, so what does grouping mean? Grouping means that we're actually going to pair the first two terms together, and we are going to look at those terms in isolation and pull a greatest common factor out from those two terms. Then we'll do the second thing with the last two terms. So really, a grouping problem takes the four term and breaks it into two pieces, and we do a GCF on that and a GCF on that, and we'll work through what happens. So as we think about this, I'm going to just rewrite what I have here. Let's look at these first two. If I look at those and pull out a greatest common factor, I can see that they share an x squared. So I'm actually going to pull that x squared out front as a GCF. So we have x squared, and then what is left behind when I do that, there's an x on this first piece and then a minus 6 on that second piece. So I have x minus 6. Okay, so this part is done. Now we're going to do the same thing over here. And when I look at these two terms, I can see that I can pull out a 2. Since this first term is positive, I'll pull out a positive 2. If this leading had been negative, I would pull out a negative GCF, but that's not the case here. So I'm going to pull out a positive 2. And I'm going to write that down. I'm pulling out a positive 2. And then what gets left behind? there's just an x that's remaining in this first piece and a -6. Well, what happens is when you do this approach and you factor by grouping, these two sets of parentheses, they should match. If this polynomial factors by grouping, these will be identical. If they're not, you want to go back and make sure you haven't made a mistake. Maybe you forgot to put it in descending order. Maybe you should have pulled out a negative and you didn't. Maybe you made a mistake. Maybe you didn't see that a 2 could come out. If this polynomial groups, these will match. And then what we do to complete the factorization, we're going to write it like this. This 2 is still there as a part of that GCF. This polynomial, we're going to write it as the product of 2 binomials, okay? What I'm going to put in that first space is this term that's in parentheses that matched. So I'm going to put that x minus 6 right there. What goes in the second set of parentheses is what I like to call the leftovers. And those were the GCFs that we had pulled out. So we take those GCFs and we literally map them into this second set of parentheses. So I have my x squared and then I have my plus 2. So that is called grouping. And so again, this GCF was out front, and this resulting 4-term polynomial, I use the grouping process to write it as the product of 2 binomials. The question becomes, are you done? Do you get to stop? If you have what's called a linear factor, and this is linear because we have x to the first, that cannot break down anymore. But if you have a square or higher as a part of your binomial, you need to consider if that will break down, and that will take you back to how do you factor a binomial. If you aren't sure how to do that, you can go back and watch the binomial factorization video. But this ends up being a sum, and this is a square, this is not, but either way, even if this had been a square, sum of squares doesn't factor. So this is an example of those binomials that is prime, and we cannot break it down. And so that means we stop. And so this is actually the complete factorization of this problem. And I would, let's box that in to say this is the result. Okay, so let's do a second example. Again, we need to decide if we have descending order, GCF, and then we'll go take a peek at the 4-term. So if I look at this example, if you look at these powers, it is not in descending order. And so that's something I need to take care of first. If I look at these, the cube is the highest power, so I need to write this term first. This would be the next power. I'll move that term second. This is to the first, that'd be my third, and then the coefficient is last. So if I just take the time to rearrange this in descending order, it's actually x cubed, there's that piece. The square comes next, and so that's minus 3x squared. And remember, when you're reordering terms, the coefficient and the sign, it does go with that term. They stay together. The third piece will then be this negative 4x. And then finally I have the plus 12. So very important, we have rearranged it in descending order. Now I look and say, can I pull out a GCF? So let me capture, that's what we did right there. As I look at these 4 terms, there's nothing they have in common. So I actually don't have a GCF to pull out of this entire polynomial like I did in the example above. So no GCF to pull out. So the next piece says what type. Obviously this is 4-term, so I am going to attempt to go group this. And remember, when we do that, we group the first 2 together and we group the last 2 together. And I take a peek at those one at a time and decide if I can pull out a GCF from each of those individually. So this first piece, if I look at these 2 terms, x cubed minus 3x squared, I can take an x squared out. I'm going to factor that out front. So let's write that. If I pull out the x squared, and then what gets left behind, there's an x from this first part and a minus 3. So that is what that will look like if I pull out a greatest common factor from those 2 pieces. Now we're going to go look at the last 2 pieces. Recall I mentioned earlier, if your leading part, anytime you're trying to pull out a GCF, if the leading term is ever negative, you actually have to pull out a negative GCF. And so if I look at both of these, a 4 is the greatest common factor that these numbers have in common. I can't pull out a variable because this term doesn't have an x. So I'm actually going to pull out a negative 4. And so if I put that GCF down and then put my parentheses to prepare to say, well, what's left behind? When you divide a negative 4 out of this, you're left with a positive x because that negative sign came out there with the 4. And when you take a positive 12 and divide it by the negative 4, we actually have a negative 3 there. If you're ever not sure if you have done this right, you could always take this GCF and distribute it or multiply it back through and convince yourself that you get the term before. If you don't get that, then there might be a mistake there. Okay, so just as in the problem above, now that I've pulled those GCFs out separately, these terms in parentheses match, which is what we were expecting. And so, again, we are going to write the product of two binomials, and these matching terms I'm going to write in the first parentheses, and then these leftovers that I had talked about before are those GCFs that were pulled out. Those are going to get mapped into this second set of parentheses. So I have an x squared minus 4. Okay, so at this point the grouping process is done and I have factored this polynomial. However, we have to do that check again to decide are we done or not. This is a linear factor because I have x to the first, so this part's done. This, however, is a square. It's called a quadratic. And anytime you have a power that's 2 or higher, you really need to ask yourself if it can break down further. And this actually can, if you know the binomial rules. This is a difference of squares, and so we would follow that difference of squares formula where I have an x that's been squared, and this is actually a 2 that's been squared. And so following that difference of square formula, we need to break this down further. So if you stop right here and you leave your answer like this, you would not receive full credit because you failed to see this last step. So I still have my x minus 3, and then this square breaks down x and x, so what was squared here goes there. What was squared there is a 2. It goes on the ends, and then one gets a plus and one gets a minus. And so these are now all 3 linear factors, and so that is what that polynomial would look like if I factored it completely. Okay, the next one I want to show is this example. This is a 4-term polynomial. If I look at it carefully, I am in descending order, so I can check that box. There isn't a GCF to pull out, and so I don't have a master GCF kind of sitting out here in front. So I'm ready to proceed to trying to group this. So if we attempt to group this, first 2, last 2, I can pull out an x squared from this first one, and I'm left with an x minus 1 behind. Again, if you're not sure if you did it right, you can always push that back through and make sure they match. Here, do you see there's nothing to pull out? One of the interesting things about grouping is you have to pull out a GCF. So if there's nothing to pull out, you're actually going to pull out a positive 1. And again, if this had been negative, I would have then pulled out a negative 1 to satisfy that rule of pulling a negative out if you have a negative leading term. So no GCF here. Have to do it though, so it's going to be a plus 1. And if you divide these by a plus 1, that doesn't change what you have in parentheses there. So this has been attempted to factor by grouping, but if you notice, these don't match. So if I go back and just verify that no mistakes were made, I confirm that indeed these don't match. And so this is an example of a 4-term polynomial that if you try to factor by grouping, it doesn't work. And this would cause us to go in an alternate direction. And you actually learn how to do this later on in college algebra when you start talking about nth degree polynomials, and you learn this process called synthetic division to help you take care of some polynomials that are set up this way. So for factoring purposes, someone might tend to say that this is prime, that it doesn't factor, at least using our traditional factoring methods. The other thing I want to point out is Why is grouping important? Grouping is actually a pretty critical skill when it comes to factoring trinomials as well, because there are multiple methods for factoring trinomials. One of the methods is called the AC method with grouping. And what that actually does is it teaches you that if you have a trinomial, so here's an example of a trinomial, it actually teaches you, again, once you've made sure it's in descending order and pulled out a GCF if applicable, the AC method with grouping teaches you how to take this middle term and actually break it apart into two different pieces. So one approach for factoring trinomials is actually to turn them into a four-way polynomial and then to factor this guy by grouping. It's a pretty neat process. So I would use the AC method, which is covered in the trinomial video. It would teach you how to do this, how to take this middle one and break it apart. And then we would go ahead and group those together and finish this problem using the grouping process. So again, most instructors or textbooks will teach you the grouping process first with a for term and then go teach you trinomials, because the grouping skills are required if you choose to use the AC method as your method of choice for trinomials. And again, I'll go through examples of how to do this in the actual trinomial video. The last thing I want to point out quickly on the for terms is there are also polynomials that are for term that you can't use grouping on. And it's not like this first example where this clearly looks like a for term. I see some x's and numbers, but I tried it and it didn't work. This is a little different. If you take a peek at this, I see two terms with x's and a number and then a different variable. When you see a problem that's set up like this, it's possible that it's another type of problem in disguise. And some instructors skip over problems like this. Some choose to include it, and we'll teach you an example of it. If you are part of an online class, a lot of times online homework systems have a problem like this in there. And if a student hasn't seen anything like this, it really throws them for a loop. But what you want to think about here is this is a four-term polynomial, but because I see these different variables, that may strike me as a little bit odd. And so one thing to consider is it possible that it's a trinomial with an extra piece? And this is the case on this one. This is actually a trinomial using the variable x, and then I have a second variable here. So we would actually factor this as a perfect square trinomial, and there's a video on how to do that, but what I want to do is just kind of show you the result and so you can see where to go from here. If you use your perfect square trinomial factoring skills, or even just regular trinomial factoring skills, we realize that this trinomial, this piece of it, this front piece, actually will factor like this. It's x plus 4 squared. And then this piece is minus y squared. And now let me do that. And if you are able to see that, you see that this is a very unique problem. It's a special case that this is actually a difference of squares problem. So you take this for term, recognize it's a trinomial with a square, and write it that way, and it becomes a difference of squares problem. And where this would be that A is a part of that formula, and this would be the B. So if you remember, difference of squares is I have a squared minus b squared, and that factors as a plus b times a minus b. And again, this was covered in the binomial video. So if we think about this whole piece as the a and this whole piece as the b, we're going to take these and map them into the formula. And so this actually ends up factoring like this. The a is x plus 4, so there's the a, and the b is the y. So there's the y, there's the y. One gets plus, one gets minus. And so this is a very interesting factoring problem. So again, when you factor four-term polynomials in the traditional sense, you are going to try grouping. you know, descending order, GCF, and then try to group. But there are a couple of special cases that it doesn't work. Again, this type, you'll learn how to handle those later in this semester. And then this is a really unique case that you learn to recognize those over time. Once you've been exposed to it once, hopefully you'll see it, you'll recognize it again if it's thrown at you. But again, just a very kind of unique case that we don't do via traditional grouping. We did kind of a modified grouping. We grouped these three together and factored it using trinomial techniques and left this one grouped alone and then recognized it as difference of squares. So I hope that's helpful. And that concludes the overview on how to factor four-term polynomials.